So last Thursday we finished up talking about splitting patterns for signals, and we said that anytime you've got a unique set of protons, you want to try to identify other unequivalent protons that are 2 or 3 bonds away, and then you essentially add 1 to that. So if you've got 1 3-bond neighbor, it will get split into a doublet. 2 3-bond neighbors get split into a triplet. 3 3-bond neighbors gets split into a quartet, and so on. The big thing that students get confused on is equivalent protons can't split each other. So that's really important. And you can't look at protons that are further than 3 bonds away. They simply are too weak to do much splitting. So let's go ahead and talk about something a little bit different, and this is called coupling constants. This is directly related to the splitting patterns that we were talking about last week. So let's take an example molecule. And for this example, I'm going to use an alkene. How many unique protons should I have for this molecule? 2, right? There's no symmetry elements in here. So what I'm going to do is I'm going to label this HA, and I'm going to label this HB. All right, and if we think about HA, what will HA be split as? Is it going to be a singlet, doublet, triplet, quartet? Doublet. It's got 1 3-bond neighbor. Add 1 to that. That means it'll be split as a doublet. So let's go down. We'll say, actually, I'm going to be more careful here. Oh, man. Sorry. I'm trying to be precise. There we go. So this is our HA doublet. And then HB, what will that be split as? Yeah, another doublet. So I'm going to do this one over here. Oop. And where do these protons typically show up on your NMR spectrum? Do you guys have that cheat sheet? So there are protons coming off of an alkene. Anybody want to help me out? 5 to 6 ppm. So we should have 2 doublets around that 5 to 6 ppm region. One's because of HA and one's because of HB. The other unique thing that occurs with these is the distance that the peaks are split are identical. We call this JAB and JBA. And basically all it means is that they split each other with an equal intensity, right? So the splitting pattern is going to have about the same width. So JAB equals JBC. And the J is just the coupling constant, and typically, should be BA. And J is a coupling constant in Hertz. So for example, if you see that HA is split and the distance of that splitting is at about 5 Hertz, that means that its partner is also going to be split with the equal intensity that's also 5 Hertz. So you got to make sure that they have the same magnitude. However, there are some weird situations that show up too. And I want to show you guys this weird situation because you might run into it. Yep?
Why are they the same if there's 2 the polling is way more like negative than polling?
So really it's just a matter of them feeling one another. It's basically saying that that peak that you're seeing at A is partnered to the peak that you're seeing for B. It's completely independent of the surrounding environment. It's just basically saying that these must be partners because they're split with the equal intensity.
Okay.
Yeah. So let's take a look at the more complicated example. Sometimes we observe weird splitting patterns. And And this makes more sense when we think about J values. So let's take another example. Let's say I've got, we'll just do the example with another hydrogen attached, where now we've got HC also here. HB, I'm going to still do in blue, and HA I've got in red. I'm not sure.
Sorry to interrupt everybody.
That's okay. I didn't see one. Sorry.
Sorry.
So how many unique protons should we have here? I kind of gave it away. 3. Why aren't HC and HB equivalent?
Because they're locked in position.
Yeah, the alkene is locked into position by that pi bond. You can't spin them around and make them equivalent, right? So HC is trans to HA and HB is cis. They're very, very different from one another. And so right now I want us just to focus on HA. So if we focus on HA, it's going to be split by HC and by HB. Typically, if we look at these, we'd say, well, we've got 2 3-bond neighbors. What should it be split as? Triplet. But that assumes that both HC and HB are similar enough where they're splitting in the same way. The reality is they're splitting in a very, very different way because they're in radically different environments. So I'll show you guys what I mean by that. So in this case, JAC, the splitting constant between A and C, is not going to be equivalent to JAB. And in this case, JAC, oh my goodness, is going to be much, much bigger than JAB. So typically, if it's trans, you're going to get a much larger splitting than if it's going to be cis. And you normally see these weird splitting patterns with alkenes, however, you occasionally see them in other systems. So I'll show you guys a simple way of looking at this. So I've got my graph paper here. This is going to be my unsplit peak for HA. I'm just going to say unsplit. All right, HA is going to be split both by HC and HB. And we know that A is going to be split most by HC because it's trans. It's further away. So what I'm going to do is I'm going to split this, and if we split it, right, that peak that was 4 units tall is now only going to be 2 units tall because it's being split into 2 equal portions. And we're going to call this splitting our JAC split. So we get split once by that C proton. And then that signal gets split again by the B proton. So this is a little bit weird. But let's imagine now this is going to get split further. And each of those single peaks that was split is going to get split one more time. So instead of it getting split as a nice distinct triplet, we've actually got these 2 sets of doublets that are side by side. So can you guys kind of see how this looks like a small doublet? The reality is when you have peaks on NMRs, they normally have smooth curves, not these sharp individual peaks. And so you've got a small doublet here and a small doublet over here. So if we look at this peak, instead of showing up as a triplet, it'll actually appear as a doublet of doublets. It's very weird to think about it that way. So this appears is a doublet of doublets. And people oftentimes abbreviate these as DD for doublet of doublets. Occasionally you see doublets of triplets. You might see doublets of quartets or triplets of quartets. When you start getting into the really, really wackadoodle ones, like let's say you've got a quartet of pentets, people normally say, whoa, that's way too much. And normally the peaks all overlap with one another into one giant blob. What would we call the peaks if it's way too complicated to interpret? A multiplet. So if you've got a really, really, really expensive NMR, sometimes you can tease apart the actual splitting pattern, but normally with your average quality NMR, it will blur so much that you'll observe just a multiplet. The one exception is doublet of doublets are observable even with relatively cheap NMRs, so you might see those occasionally. It's a weird phenomenon, but normally it only happens when the coupling constant is really, really different, and you see that often with alkenes.
So what does that look like if you dry out?
Yeah, that's a good question. So if you were to look at this, you'd have a small doublet adjacent to another small doublet, but this would be in a really close ppm range. So they'd be side by side right next to each other.
Okay.
If you imagine a triplet, all really a triplet is two doublets of doublets that have been merged together so that the center peak is overlapping. It's a little bit weird to think about, but the splitting pattern is the exact same for a triplet. It's just that those inner two peaks are now overlapping and they're twice as tall.
But in this case, they're not.
Yeah, in this case, they're not overlapping. Yeah, it can make your head spin a little, but we're going to focus primarily on the elementary examples of NMR. All right, just a couple more sections. The next one is interpreting or anticipating chemical shift or resonant frequency for NMR. And we have to define this first. Chemical shift used to be defined as tau. It was an old unit used in like the 1960s, and then gradually we've moved away from that and we use ppm, or parts per million. And so let's define how we calculate parts per million. And chemical shift, parts per million, is normally abbreviated with a lowercase delta. And it's the observed shift from TMS in hertz times 10 to the 6 divided by the operating frequency of your NMR. This will help you with a sapling problem, hint, hint. Divided by the operating frequency of your NMR that you're using in hertz. So depending on your NMR, it might be a 60 megahertz NMR, which is what we have in our lab, or it could be all the way up to a gigahertz NMR, which you might see in a really, really high-end protein lab. Most NMRs nowadays in small research labs are about 400 megahertz. So our NMR that we have in our lab is considerably smaller and considerably less powerful. Usually the larger the magnet in your NMR, the higher quality NMR spectrum you'll get. What do you guys think TMS is? Oh. So TMS is tetramethylsilane. And really, this is just our standard that we've identified as being 0 ppm on our scale. We just arbitrarily said this is always going to be 0 regardless of which NMR you're taking your sample on. So you can imagine this is a really nice thing to use because all of the methyl groups coming off of here are equivalent. And this is a super duper non-polar molecule, so this is going to get out of the way of everything else. So this is defined as 0 ppm, the protons coming off of here. Oftentimes when you've got your solvent that you're taking your NMR sample in, you'll spike in a little bit of TMS just so you have some sort of reference standard. Going off of that, when you're taking NMR spectra and you're picking out a solvent, what's the most important feature that your solvent must have? Does anybody know based off of the book? Deuterium, right? Why do we have to pick a solvent that only has deuterium atoms in there?
Organic solvents are a lot harder.
Yeah, so if we think about, let's say I want to do my NMR in water, right? All you're going to see is the peaks for the protons on your water as a solvent molecule, right? Because NMR can see protons, but it can't see deuterium atoms. So you want to choose a solvent that has deuterium because it's invisible by NMR. That's the most important thing when you're picking an NMR solvent, is pick something that's NMR silent. So deuterated solvents work the best. So let's take a look at the scale here. Typically, we have the scale from about 0 to 12 ppm. You can also measure it out in hertz, this scale, but almost every single NMR that you see will be measured in ppm. And TMS is always going to be down in this region. The question now is whether or not your peaks will show up more to the left-hand side or more to the right-hand side. I gave you guys that cheat sheet, but there are some really easy tools you can use to predict where your chemical shift will show up. So I'll show you guys the two main properties. Does anybody think they know the first one? Electronegativity, that's a big one. So electronegativity is a really easy way of predicting chemical shift. So if you think about this being about 0 to 12 ppm, typically the more polar molecules will show up a little bit closer to the higher ppm numbers. And this occurs all the way up to about 5 ppm-ish. And then the less polar molecules typically show up closer to 0 ppm or 1 ppm. So if you guys remember induction too, induction trails off the further away you get from electronegative atoms. So you can use inductive effects to predict the relative order of your peak sequence too. So if you've got a set of protons closest to oxygen, they're going to be at a higher ppm than the protons 1 carbon away, right? So that's a really good way of trying to predict your order of peaks in your NMR spectrum. So electronegativity or induction is one. It's a really rough tool, but it works. The second one is really important because it's a dead giveaway when you're trying to narrow down compounds, and that's aromaticity. And this has a fancy name called the anisotropic effect. And we're going to talk a lot about aromatic molecules next term, but I'll give you guys a sneak peek. Let's imagine that we've got this side-on view of a benzene ring. All right, so I'm going to draw one face of it kind of wedged. The other face is kind of sticking back into the plane. You guys kind of see that, how it's a benzene ring on its side. If you think about this, right, there's a bunch of p orbitals sticking up and down. And we know that there's a ton of resonance in these benzene rings. So you've got this circulating flow of electrons both above and below the plane of the ring. When this happens, you actually create a little miniature magnetic field. So this magnetic field, because we've got moving electrons, is kind of going through the center of your benzene ring and around the sides. That means that the protons that are in this environment behave pretty strangely because they're in the midst of their own little magnetic field due to the aromatic ring that they're attached to. And these always show up in what range? Does anybody know? 6 to 9. At least for simple cases. So let's take a look. We said 0 to 12 is our typical range. These typically show up around 6 to 9 ppm. For aromatic protons. If you start taking advanced chemistry classes, you can start getting into weird anisotropic effects where it will go all the way up to like 20 ppm under super bizarre situations. And then there are other situations where that weird induced magnetic field will pull it all the way to negative ppm. So normally we don't run into those. Normally we are just looking for this aromatic region with simple benzene rings or simple aromatic rings. So if you do see peaks in that 6 to 9 region, that's a huge clue that you've got some sort of benzene ring in there.
Will you see that weird stuff if you have like fused benzene rings?
Yeah, so if you have fused benzene rings, it depends. It qualifies as aromatic, and we'll define aromaticity next term. If you have an anti-aromatic system, all bets are off. Your protons could be all over the place on your NMR. Okay, so I'll show you guys one last thing for predicting chemical shift. It's something that I've really only seen in our textbook, which is pretty nice, and it's at the end of our chapter. And he's got this nice little chart for really accurately predicting where protons will show up. So what he does is he says, identify your benchmark value. Your benchmark value is basically whether or not your carbon that the protons coming off, or your protons coming off of, is primary, secondary, or tertiary. Can you guys see that? So the methyl protons are typically at about 0.9 ppm. That means if you've just got a plain old vanilla methyl group, your peak will always show up at about 0.9 ppm. If you've got a secondary carbon with nothing else nearby, it's always going to show up at about 1.2. Tertiary carbons are always at about 1.7. But we know that if there are any polar elements or functional groups nearby, that will shift things to a higher ppm, right? Because of that inductive effect. So the next thing he says is, well, oxygens are super duper electronegative. So if you've got an oxygen attached to that carbon, you have to add 2.5 ppm to that value. So for example, he's saying if you've got this secondary carbon right here, the benchmark value is 1.2, right? And then you add in 2.5, that means these protons will now show up at about 3.7 ppm. This is astonishingly accurate. It'll give you usually the correct value within a half ppm or so. It's really good at identifying your unknown proton. The other one is if you've got protons on a carbon next to an ester, then you want to add 3 ppm. So in this case, our benchmark value for protons coming off of a secondary carbon is 1.2. You add 3 to that, now it's going to show up at 4.2. So you can really easily identify, hey, this is most likely a set that's attached to an ester if it's showing up in that 4 region. If you've got something on a carbon that's directly attached to a carbonyl, you only add 1 because it's not nearly as electronegative as an ester. So this is a really useful tool. And if you guys are struggling with determining possible isomers that match your NMR, try to break this out and see which one matches your NMR frequencies the best. Does that make sense? It's kind of a nice trick that the Klein textbook has that I don't think any other textbook I've seen has in there.
Stefan talks about downshift and upshift. Is downshift referring to like higher ppm?
Oh, that's a good question. So downfield
Or downfield, my bad.
typically means a higher ppm. Upfield means a lower ppm. It's used synonymously for high or low ppm. So downsfield's always a higher ppm.
But we're going to get into like shielding today too.
So shielding is related to that anisotropic effect. So if you're an aromatic proton, you're always going to show up in this region, and that has to do with that induced magnetic field. But yeah, for right now, just worry about downfield and upfield or high ppm and low ppm. Yep.
On the table at the bottom, all the way down, whatever one you just showed us. Yeah, that one. Should be. He was saying that if it's another carbon over, or he said to do 1/5 of whatever that value is.
Yeah. So
Does that still work?
you can. So the question was, if you're not an alpha proton, meaning you're not directly attached to these functional groups, but you're one further away, that inductive effect drops off really, really rapidly. So you can tack on 1/5 of these add-on values. Yeah. However, normally that's pretty minuscule, especially when you're talking about like a carbonyl group. 1/5 of that is what, 0.2?
Yeah.
So it's
Not that useful.
yeah, it's not super useful. The benchmark values in and of themselves are really useful though. All right, so the last section, carbon-13 NMR. Carbon-13 NMR, we will see on occasion. It's useful to some degree, but it's a little less useful than proton NMR. There are some key features with carbon NMR. The first one is that it is less sensitive. Why is carbon-13 NMR less sensitive than proton NMR?
It's only 1.1%.
Yeah, it's 1.1% abundant. That means that if it took us, let's say, a minute to collect our spectrum for a proton NMR, it's going to take us over an hour to get a carbon NMR. Oftentimes with carbon NMRs, with cheap spectrometers, you actually have to run them overnight in order to get a decent quality scan. We are not going to do that during our lab. So if you have a really nice NMR, you can get carbon NMRs pretty quickly, but even then it takes longer than usual. The other thing is that there's no splitting. Everything's a singlet. Which makes things considerably easier. This is true for a simple carbon-13 NMR. The other thing is that there is no integration. The integration values, so if you measure the area underneath carbon NMR peaks, isn't going to tell you very much. It'll be way off from the actual number of carbons that make up that peak. However, it does tell you some important information. It tells you the unique number of carbons. So kind of like we did on that pod a couple days ago where you guys predicted the number of unique carbons, you should be able to identify the number of peaks corresponding to that in your carbon NMR. And then the last thing is that the chemical shift corresponds to functional group. So I'll show you guys what I mean by that. If you go back to that cheat sheet that I gave you, that NMR study guide, and you go to the carbon NMR section, you can see that if you're looking for a carbon that is a carbonyl carbon, almost all of them show up in this really downfield region from about 160 to about 220 ppm. So you can see the scale for carbon NMR is much, 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 much bigger than proton NMR. It goes from 0 to 220. Typically, these show up really far downfield, and why do you think that is?
The carbon double bond.
Yeah, if you think about the dipole there, that's a really, really, really strong dipole. So these show up way downfield. And then you've got your aromatic carbons. They show up at around 120-ish. Same thing with alkene carbons, and triple bonded carbons show up in this region from about 80 to 140 ppm. So you can see, you can roughly correlate these, but it's not super predictive unless you get into more advanced NMR experiments. Then next you've got single bonded carbons with some sort of electronegative atom attached. So you can imagine X is a number of any electronegative atoms, whether that's fluorine, bromine, or chlorine. And then you've got your tertiary carbons showing up at a much more lower ppm frequency, and then secondary, and then primary. So you can use this to at least roughly approximate what you've got going on. One thing I really like about carbon NMR is it will tell you a lot about symmetry, right? So let's say you've got a molecule with a molecular formula of C6H12, right? And let's say you only see one carbon peak in your carbon NMR. What does that mean?
Cyclohexane.
That means there's a lot of symmetry going on. And chances are the higher degrees of symmetry you have, it's a clue that it's cyclic. And so cyclohexane, for that matter, has 6 degrees of symmetry because you can rotate it 6 different directions and end up with the exact same molecule, right? So you can use it to identify how many planes of symmetry you have or deduce whether or not you likely have some sort of cyclic system. It's a pretty powerful tool. So like I said, this study guide will be available to you on the exam. And during second term, I'll give you guys this. So it will be projected up on the board, or if you're taking it somewhere else, it'll be available as a separate handout. So you can use these as a really powerful tool. Yep,
Front and back?
front and back. Yeah. At this point, I want you guys to get really good at interpreting NMR. That's the most important thing. All right, so I'm going to shut off the recording. But before I do, I want to show you guys this in-class activity that we're going to work on today and tomorrow. And this is available on the website. And what I've given you guys is a molecular formula and then the corresponding proton NMR. What do you think the first thing you could do without knowing anything about NMR is? What did you guys do for mass spec when you had a molecular formula? HDI, right? So first thing I would do is calculate HDI. That tells you the number of rings and pi bonds. After that, then look at your NMR and try to find the clues that are helpful. So for example, in this first NMR spectrum, it's C6H6, which has an HDI of 4. Pretty high HDI. So that means we've got some sort of combination of rings and pi bonds that adds up to 4. And then what do you notice about this peak showing up between 7 and 8 ppm? It's in the aromatic region. The fact that we're only seeing one peak means we've got some sort of symmetry going on. What do you guys think this molecule might be? Benzene, right? So this is kind of the systematic way you've got to go through these, but what I'm going to do is hand out these worksheets, and I really recommend working on these together. You can work on them overnight too, and I'll have a new set ready for you guys tomorrow as well. All right, let me shut this down.